is the Erdős stone that for r greater than 0, greater than 2, and s greater than 1, in every epsilon there exists an integer n naught, such that if n is greater than that, if the number of vertices is greater than n naught, and having at least, so every graph with n vertices and at least tr minus 1 of n plus epsilon n2 edges contains your R-partite complete graph as a subgraph. So one very important note is that any large enough bipartite graph with equal partition sets, fixed positive edge density, however small, and a uniform distribution of edges will contain any given bipartite subgraph. So edge density of G, this forces, so if it is big enough, then occurrence of H is probable, is obvious. And so H, your subgraph, is the union of all bipartite subgraphs, and this is the union of induced by pairs of color classes of coloring of H. And asymptotically, I can say that asymptotically you need TR minus 1 edges to force the graph having R-partite complete subgraph with S vertices in each independent set. And just the corollary of Erdős and Simonovitz, 1966, it says that for every edge, at least one edge, we can say that extremal number of n and h is related to its chromatic number. Chromatic number of h minus 1 plus little o 1 and choose 2. So now Erdős and Simonovitz in 1966, they showed that how extremal number of any graph, not just triangle, not just, for example, R-partite graph, any graph, is related to the chromatic number of that. So chromatic number forces the maximal number of edges without having a copy of H. And now let's just prove it. The proof is very simple, because you just let R equal to chi of H, and that's it. You know, H is not a subgraph of, we know that H is not subgraph of Turan for any n. Because remember, Turan 9041 says that extremal number of n and kr, Turan, when it says Turan, always think of your complete R-partite graph. This is equal to number of edges is less than equal to 1 minus 1 over R minus 1 and choose 2. And hence, extremal number of n and h should be greater than equal to tr minus 1. On the other hand, h is a subgraph of KRS. You have R partition, and S is the number of vertices in each independent set. So S is V of H. And the final thing is that extremal number of N and H is less than equal to extremal number of N and your complete R-partite graph, which is equal to Turan plus just a little open question, order of N2. This is open question. We just say that this is order of that. We don't know exactly how much. So the proof is complete. To prove the Erdős stone, we need to define what is regularity graph. What is regularity graph? So let G be a graph with an epsilon regular partition. In other words, we have your garbage bin because it could not satisfy epsilon regularity, but the rest of them pairwise they satisfy. Most of them satisfy, and V1 is equal to Vk except V0 because V0 is not good. All of them are have size L. So the size of any independent set is L, and the regularity graph of G with parameters epsilon L D is the graph where V of R, vertices of R, are just V1, Vk. So E of R, by definition, is that all the edges that Vi, Vj is an epsilon regular part of density. Remember, we have a parameter D, and your density should be at least D. And we throw away irregular pairs, so the remainder is E of R. So E of R is a particular edges that we have epsilon regular of density greater than D. So we are picking just big densities. We are just selecting big densities. And we throw away irregular pairs. And the S blow up, this is the definition, S blow up of R by definition is that every vertex Vi is now replaced by a set of VIS of S vertices, and every edge is replaced by a complete bipartite graph. So the blow up lemma, it says that for any D and delta greater than 1, so your maximum degree is greater than 1, there exists an epsilon naught greater than 0 such that if G is a graph and R is a regularity graph of G with parameters epsilon L D, and H is a subgraph. H is a subgraph of RS, and the delta of H is less than equal to delta. then H is a subgraph of G. So blow up lemma, it only tries to say that your new H, which is a subgraph of S, is a subgraph of G. But provided that epsilon is less than epsilon naught and L is bigger than something, d to the delta. So this says that your pars are large enough. They are large enough. And finally, the last things that we need to prove Erdős stone is that we need to define nk of y, which is by definition all the vertices of graph G such that the neighbors of V, you have at least k neighbors in Y. In other words, this is greater than. It means that you have B, you have A, then if it is N, your neighbors of Y, so any point here goes to many vertices, at least k vertices. And you have d minus epsilon times y neighbors, at least. And so the rest of them, the shaded area is A excluding your neighbors of Y. So epsilon regular pair, so the lemma epsilon regular pairs, it says that let A and B be an epsilon regular like this and this, epsilon regular pair of density D. If Y is a subset of B, like this, Y is a subset of B, which is relatively large, then the lemma says that the cardinality of A, excluding N, I mean the shaded area, this cardinality is less than epsilon cardinality of A. It means that all of the important vertices are in set N. And the proof of Erdős stone is the last things I want to say about these extremal graph theory. So let D to be gamma and delta to be delta of KRS, and we choose epsilon as small enough, and we choose L to be greater than 2s d to the delta, which is large enough, in other words. So if R is a R is a regular by definition. It's a regular graph of G with parameters epsilon LD. So there are just two cases. In case one, we are very lucky. Case one, R contains, and we don't have any argument because it contains your apartheid graph. Then just use blow up lemma. Use blow up lemma, and so G contains H, which is apartheid complete graph. And so we are very lucky. But in case two, if R does not contain your apartheid complete graph, then by two-round theorem, the number of edges of R is less than t, the two-round number of k, which is less than 1 minus 1 over r minus 1, k choose 2. But we can say that the cardinality of the edges is at most E of r L2 plus epsilon N2 plus epsilon K2 L2 plus d K choose 2 L2. And let's say what are these? So this is the low density pairs. Low density pairs. Because we have worked on the N set, if you remember. So we have low density pairs, and this is our irregular pairs. Irregular pairs. We have k squared, L squared of them. And then we have, this is trash, because the edges incident with the, this is, I call it the trash. And so this is less than equal to this, and this is less than equal to T r minus 1 of n plus gamma n2, and this is a contradiction. And now, so I have talked about extremal graph theory. Extremal graph theory. We have spectral graph theory, which is a kind of very algebraic approach. So for example, things like Shiger constant. What else can we say? Eigenvalues of second eigenvalues, or even higher eigenvalues of the degree matrix minus A. Your Laplacian, I mean. Laplacian, the eigenvalues and eigenvectors of Laplacian. So because the spectrum shows the different structures. For example, if you have if you have some obstacles or something, some big giant entities, some big connected components, and it reveals the structure of a graph. It's like an eigenvalue and eigenvectors of a matrix in linear algebra that decomposes your space into some subspaces. It is the same idea, but you should be very careful to use it for very large graphs. Because in very large graphs, first of all, the calculation is quite difficult. That's the motivation behind construction of a kind of expander graphs. I mean, the expansion ratio, for example, this is vertex, expansion ratio is very high. They are very connected, and they are not very, very sparse. They are not very sparse, and they are not very dense. Something between, but it has a lot of connections. And there are many articles on how to use them. For example, Zigzag, I forgot that Israeli guy. He had an algorithm to construct expander graph based on Zigzag. And so I want to say that there are very different methods for graph theory. Also, recently graphones, which is interesting if you want to extend the discrete graph to infinite graphs, finite graph to infinite graphs. And it uses graphones, for example,